So let me revise what all charts we have seen. So when we have simply some numbers, we can draw what is known as dot plot or individual value plot, which will give us some idea about the spread of the data. We also saw it can give us some patterns. For example, there are hardly any females driving above this speed but many males driving above this speed, etc. Bar plot is where I have some categories, or for example here countries, and for every country I have one value, or if I have frequencies for each country of something, counts of something, then I can draw bar plot. Then histogram is when I have some continuous variable like sleep duration. So people can tell me I slept for 4.5 hours or 3.25 hours. So for such representations we use histogram. So every bar in the histogram, that height represents frequency. What is happening? Okay, so the height represents frequency, and this interval. So for example, there are 11 people who slept between 9.5 to 10.5 hours, etc. Such histograms can many a times be overlaid with normal curves. Normal curve, we are have you learnt normal curve in the mathematics part of this paper? Yes or no? Hello.
Could you please repeat the question?
Have you studied normal distribution in mathematics part of this paper?
No, I don't think we have.
Okay, we will see. Anyway, we are going to use it. Then another important point about this was that this is a symmetric curve, whereas if you ask, because this was about sleep patterns, so most of the people sleep, their sleep duration is near average, very few people on either extreme. Whereas if you ask question like computer usage last week, you might get a non-symmetric distribution. So there are few, most of the people used computer for a very small time, whereas there were still some people who used for a very long time, unexpectedly long time. So this is known as skewed distribution, positively skewed distribution. And you cannot fit a normal curve to such skewed distribution, it would give you bad results. And then we saw box plot. In box plot, we saw that this is q1, means this is first quantile. So below this border, below this bottom border of the box, there are only 25% values. Above the top border, there are only 25% values. So 50% values are in between. This purple line is median. So this divides the observations into two parts, 50-50, and this is mean. Okay. And then we also saw pie chart. Pie chart everyone knows, and just now we have seen this. Now, so here I saw some examples of ready-made graphs. When you are just seeing graphs, everything looks very easy to do. But there are many things which can go wrong when you are trying to draw graphs. So we need to know those so that we don't repeat those mistakes when we are drawing graphs on our own. So what all can go wrong? First is, we should always remember that proportionality is important. We cannot draw willy-nilly pictures. So this is taken from some newspaper in US. So the government was deciding on imposing some tax or something like that, and then this newspaper probably was from the other political party, so they wanted to irk people. So they printed this picture saying that government is, cutting down our income by 3.4%, and it is cutting through our income, so we are going to have to suffer a lot, etc., etc. But now you people also know percentages. So considering these notes, is it really 3.4% this portion? No. If I draw proportionate picture, 3.4% would look something like this. Okay. This is almost like 34%. So you should not draw such misleading pictures, okay, just because you want to emphasize your point. We should always keep the sense of proportionality in our mind while drawing such graphs. Then in pie chart is a very easy tool, everyone likes it. But how many sectors should be there? So this is based on monthly rainfall data in Pune in 2007. Now we can see that obviously June, July, August, September have large chunk of rainfall. They are monsoon months, but all the other months are clubbed in this. So is it really necessary to name all the months and keep them as separate petals? Because we can't really even figure out what is the contribution of each petal. So ideally, we should do something like this: June, July, August, September, and then all others combined in one small sector. Okay. So in a pie chart, we should always keep in mind that only the important categories should be in sectors. Rest of the categories can be clubbed as miscellaneous or others, something like that. This is another interesting example. So again, this is from US, uh, old example. So again, some newspaper printed a graph saying that Japanese multinationals are investing too much in US and they are going to take over our economy, and consequences would be bad, etc., etc. And he printed this graph in support of his conclusion. So he said to people that, see, initially the Japanese investments were increasing in a gradual manner, but in the past few years there has been a very steep rise, very sudden rise. Okay, so this part of the curve is very steep slope. So people started saying that yes, 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 there is something to be done. What he conveniently ignored or forgot, I don't know what happened, is the scale on the x-axis. See, this is 70, 71, 2, 3, 4, 5, 6, 7, 8, 9, 80, and after 80 suddenly the next value is 85 and 90. So what is happening is 75 to 85 year period had actually this length. So ideally 80 to 85 should also have that much length. But because you are compressing the scale suddenly, things are becoming bad. If I redraw on the corrected scale, then the graph doesn't look that bad. Okay, here it was initially almost flat and then very sudden jump, whereas now here there seems to be almost consistent increase, not too bad or not too alarming jump. Why? Because now we separated 80 to 85 into actually 5 unit space. Now you would think that why did this person draw directly 85, why not 81, 82, 83, 84? Now the problem is, like many real data sets, there will be missing values. So he did not have values for 81, 82, 83, 84. The, and that is bound to happen even with you. You may not have all the values required. But you have to still make sure that missing values don't become a misleading factor in your graphs. So if you don't have values, keep those points vacant and then join them, or join it by dotted line if you want to say that this trend is not completely confirmed by data. So join it by dotted lines, but do not drop points on x-axis just because you don't have data on them. Okay so far?
Yes, ma'am.
Another important point is importance of zero. What do I mean by importance of zero? So this data come from Olympics. Okay, Olympic 500 meters speed skating data. So these are winning times in seconds. So you can see in 19 around 1930 etc., the winning time in seconds was above 42.5 seconds, and now in 1995 etc., it has decreased. So if I look at this picture, it seems like a very very sharp decline. So does it mean that human performance has improved so much over such a small span of year, that he or she that every human, the players here have become very fast? But then that seems unbelievable. We have not had that much change in our capacities, physical capacities. Then what is happening? Of course there are some additional resources for help, like more ergonomic shoes, etc., etc., but still it shouldn't change in general human power by such a large in general human body capacity by such a large margin. And then if I add 0 to the data, then things become clear. When I add 0, I can see that this decline is not as sharp decline as it was seen here. Okay, so once I add 0, once I rescale the data, it seems that okay, this is not very sharp decline, and it is okay because as I said, people have been improving from the sport technology angle. So your clothes, your shoes, all of them help you in gaining speed, and then of course effect of that is seen here. So in such, whenever you want to make such comparisons, 0 should not be avoided. Okay, another thing is, actually this graph tells you two things. First of all, extrapolation is always dangerous. Okay, so if I know something about certain range of the data, it may not really work for other part of the data. Hence extrapolation is always dangerous. And second point is, in scatter plot sometimes you may see other patterns also. For example, in this data we have fitted a regression line to estimate US population. Okay, US population in million over the years. Now you might say at the first look that this um, okay, so you might feel that this fit is good because we are going to learn later that this R square actually indicates whether the fit is good or bad, and 100% is of course the best. So R square of 92%, and you can see that these points are pretty close to the uh, red line. So it seems that the model is working. But the problem is, if we do predictions here, so there is some mistake here. Okay, there is a typing mistake. Then prediction for 2050 turns out to be 294 million, and prediction for 2020 turns out to be somewhere around 250 million or even below that. Okay, slightly below 250 million. But the actual 2020 population is 331.5 million, because initially the pattern was up to this, but the pattern has suddenly changed. Okay, so what to do? In such cases, we have something called as quadratic regression or polynomial regression. So now we fit a quadratic regression model, and we can see that the fit has improved significantly. Okay, and now if I try to predict, prediction for 2050 is 428 million, prediction for 2020 is 333 million, and actual 2020 population is 331.5 million. So these two values are pretty much in agreement with each other. Okay, so these are some of the these are some of the points which you need to keep in your mind when you are trying to draw graphs on your own.